All right, guys. So in today's video, we're going to be talking about how to conduct a significance test for a population mean. Let's start by talking about what conditions have to be checked in order to perform this significance test. The first two are actually the exact same as they are for a proportion. We've got to make sure that it's coming from a random sample or a randomized experiment, as well as 10% condition. We've got to make sure that our sample size is no more than 10% of our population. A reminder that that is what checks for independence and allows us to calculate standard deviation. Now, the one that is slightly different is how we go about establishing a approximately normal sampling distribution. We don't use the same large counts. There is no proportion to multiply n by to be able to do that for a mean. So instead, we've got a couple of options. Option one is if it does tell us somewhere in the context of the problem that the population is normally distributed, then we can say the same about the sampling distribution. If not, then we've got to use the central limit theorem, which says that it will become approximately normal as long as the sample size is at least 30. Now, remember there is kind of that third scenario where if neither one of those is the case, but they provide us with the data, we can always graph the data and check for ourselves. Is there any skew or outliers that would prevent us from continuing? So when we talk about differences as well, we also need to talk about the test statistic. So the test statistic is still found in a similar way. You take your statistic minus your parameter divided by the standard error of your statistic. Here, though, it's going to be slightly different because we're once again going to be using t. So the same way that we use t star as our critical value for confidence intervals for a mean, we're going to be using t as our test statistic, unless we know the population standard deviation. Remember, that's where we can continue to use z as our test statistic, again, similar to z star for a confidence interval. As for the p-value, interpretation of that is still the same. That is the probability that your sample will take on values that are either as extreme or more extreme than the one that you found in the sample. Okay, so let's talk about what we're going to need to go through and make sure we understand the four-step process as it relates to a mean. So the first part is our statement. In our statement, we are going to first mention our parameter of interest, which remember in this case is mu. We're also going to mention our hypotheses, our null alternative, as well as the significance level alpha. Remember that we're going to assume to be 0.05 unless it tells us otherwise in the context of the problem. Next, in the plain step, we're going to mention what test we are doing, which is a one sample t-test. Well, that might not seem like an important thing as of right now because we've only had one proportion z test and now one sample t-test. Throughout the course of this term, we're going to see a lot of other tests, and it's going to become more and more important that we understand which test we're using and why. Next, we're going to check those conditions we mentioned at the start of this video, so randomness, 10% in large counts, or rather the central limit there. Next, in the do step, we're going to find our test statistic t, use that to find our p-value, and since we are using the t distribution, notice we've got to be careful and make sure we mention the degrees of freedom. Remember, degrees of freedom is simply one less than your sample size, and that's important because the t distribution is different depending on the sample size. So that's one difference between it and the population proportion where we use z. All standard normal distributions look the same. That is not the case for t. Last but not least, in our conclusion step, we're going to say whether or not we're going to reject our null hypothesis, and then also make sure we provide that in context. Okay, so before we actually go through and do a significance test, let's make sure we can find the appropriate p-values using our graphing calculator. So keep in mind for each of these examples, while it gives us n, we are really interested in the degrees of freedom, which is one less than that. So for our first example, degrees of freedom will be 14, and for the second, degrees of freedom will be 9. So in our calculator, we're going to be able to find these by using the distributions menu of our calculator. So second vars to get there, and then we're going to be using TCDF because we're looking for the area under the curve. So in the TCDF menu, it's going to give us a few different things that it wants. The first thing that it wants is the lower value. So if I want to, for this first example, find my p-value where t is greater than 1.54, 1.54 would be somewhere over here to the right, and we're looking for area to the right, meaning 1.54 would be my lower. For upper, pick something very, very large. And then for degrees of freedom, we just mentioned that. Make sure that we put in 14. Go ahead and press paste, and your calculator will run through the calculations for you, and you'll find out that your t is about 0.0729, which gives you that as the p-value. So If that was our p-value and we were doing a significance test, assuming our significance level is 0.05, we would be failing to reject in this case. Next, let's look at the probability that t is less than 0.94. I'm not going to draw a picture for this one, but you could if that would help for you. In this case, our lower is going to be picking something infinitely small. Upper is that 0.94. Degrees of freedom is 9. So let's go ahead and get that typed into our tcdf command. So I'm going to pick something, again, very, very small. Upper 0.94, and now degrees of freedom, don't forget to change that to now be 9, is going to tell us that our area to the left is going to be 0.814. So definitely going to be failing to reject in this case, regardless of significance level. You would never have a significance level that was really higher than probably 15 or 20% realistically. Okay, so let's take a look at an example going through the 4-step process and making sure we know how to do that for a mean. The context that we're going to be looking at is going to be the dissolved oxygen level in a stream or river, which is an important indicator of the water's ability to support aquatic life. So a researcher measured the DO level at 15 randomly chosen locations along a stream. Here are those results in milligrams per liter. It tells us in this context as well that a dissolved oxygen level below 5 milligrams per liter would put aquatic life at risk. So that would most likely be the claim here. So in part A, do we have convincing evidence at the 5% significance level that aquatic life in this stream is at risk? Let's go through that 4-step process. So step number 1, let's write out our statement. So we're going to say mu is the true dissolved oxygen level of the stream. And then for our hypotheses, the null hypothesis is going to be that mu is equal to that 5 milligrams per liter that they provided to us. Our alternative is we want to know if they are at risk, and it says a level below 5 milligrams will put them at risk. So we'll have a one-sided test here that the mean is less than 5. And then last but not least, our significance level, it does actually tell us to use 0.05. We would have been using that anyways. Okay, so there is our statement. Next for our plan, let's write out, first of all, what type of test it's going to be, which is a 1-sample t-test. And then let's go ahead and check our conditions for it. So the first thing we need to check is whether or not our data is random. It does say that they were from 15 randomly chosen locations, so we should be good there. Next would be our 10% condition. If we take 10 multiplied by our sample size is 15, is it reasonable to assume that we could have checked more than 150 locations along the stream? And I would say that's a pretty safe bet. Last but not least, it does not say anywhere in this problem that the population is normal, and unfortunately 15 is not at least 30. So this is going to be one of those times where we actually have to graph this data and look to see if it is approximately normal and make sure it doesn't have any outliers and skew and things like that. So in the stat menu of our calculator, let's go ahead and edit. Let's get rid of any data that's in there. So clear out your list 1, list 2, and so on. And we'll go ahead and start to type these numbers into list 1. So if you want to fast forward in the video so you don't have to watch me type the numbers in, you certainly can. Okay, I've got all those numbers typed in. I'm just going to run through and make sure I didn't make any typos real quick here as well. So if you want to fast forward the video a little bit more, I'm just going to be going through and checking all my numbers. I would encourage you to do the same, maybe as you are watching here. All right, looks like I've got all my data in there. Let's see what it looks like on my graph. So I'm gonna go into my plots menu. Let's turn on plot number 1. And I prefer the histogram. It just makes it easier to tell what the shape of the distribution is. For X list, let's make sure that's list 1. And then before I graph it, I'm gonna going to go back into my y equals screen. Just make sure, like here, I've got some other stuff there that I don't want, that's cleared out. And then remember to zoom in on it. We're going to choose zoom 9 for zoom stat. That way we go straight to all the data. So looking at this data, we're looking for obvious signs of skew. I don't really see that here, or outliers. So what I'm going to say is that the histogram of the data shows no skew or outliers. And then remember, this is where we can say that we're going to proceed with caution. Okay, so we're done checking everything for our data here. We're ready to proceed with our calculations. So first is we need to go ahead and calculate our test statistic t. In order to do that, remember, we're going to need both our sample mean as well as our standard deviation for our sample. So it's a good thing that we've got all of our data typed in to list 1, because we can go into stat, over to calc, and run one of our stats in order to find each of those values. So it looks like the mean for my distribution here is 4.77 minus, remember, the claimed mean of 5 over my standard deviation S of x, which it tells me is 0.94, divided by the square root of n, which is the square root of 15. So let's go ahead and figure out what that's going to give us now. So in my calculator, 4.77 minus 5 is negative 0.23. I'll then, for my denominator, take 0.94 divided by the square root of 15 is going to be 0.24. And so then I'll take my negative 0.23 divided by my 0.24 is going to give me a test statistic t of negative 0.95. Next, let's find our p-value for this distribution. So for the p-value, remember, this is where we're doing t-CDF to find that. In this case, we want it to be less than that value, so we need to pick something very small up to that negative 0.95, and then degrees of freedom, in this case, one less than our sample size, would be 14. So let's go into that distributions menu like we did previously. We'll choose t-CDF here. Lower I've already got there, so negative 0.95 for my upper, and then 14 for my degrees of freedom is going to give me a p-value in this case of 0.179. So now that we've got all of our information, we're ready to draw our conclusion. So in our conclusion step, we're going to say that because the p-value, which the p-value in this case is 0.1, I'll go just 0.18, is greater than our significance level alpha, which was 0.05, we are going to fail to reject our null hypothesis. In other words, there was not convincing evidence that the dissolved oxygen level of the stream was below 5 milligrams per liter. Okay. So in part B now, it says, given our conclusion that we just wrote, what kind of mistake could we have made? And explain what this mistake would mean in context. By mistake, it means what potential error could have occurred. And it's not saying what could we have messed up. It's simply saying what did the evidence not help us to find. In other words, did we make a type 1 error or did we make a type 2 error? Well, just as a reminder, type 1 is when you reject the null hypothesis when you should have, which was not the case here. Type 2 is when you fail to reject the null hypothesis when you should have. So in this particular problem, a type 2 error is the error that could have been made. Now, what would this have meant in context? Well, that basically means that the null hypothesis was wrong and we should have gone with the alternative. In other words, the dissolved oxygen level really was below 5 milligrams per liter. Now, in context, what that could mean is that the aquatic life may be at risk. And unfortunately, the data didn't support that. So unfortunately, that aquatic life might not be able to survive much longer. Okay. Guys, we will save this next example to start our next class period. So have that one ready. That will become our warm-up the next time I see you. Until then, have a good rest of your day.